evaluate f of negative 2 if f of x equals all that stuff. All right. The first step, I would imagine, in order, just thinking in terms of credit on a regents, you need to show all work, that kind of stuff. You're gonna want to write at least something along these lines. But from here on out, you're able to use your resources. So I look at it like, all right, is there a reasonable expectation that a single person in any one of my classes could figure this out without showing any additional work? Like, is there a person in any of my classes who can just read this from left to right and come up with the answer in their head?
No.
How would you know?
Because I'm a wizard.
Oh, okay. Well, I mean, in light of that new information, it changes everything. The answer is yes. There definitely is somebody who can run these numbers in their head. If that's the case, then it's okay to just write the answer from here. Anybody know what that answer is?
4.
4?
Well, actually, I'm a wizard.
Yeah, well, which one is it? Because I'm getting confused. Wizard or God of wizards?
I'm a wizard, but I'm also a god wizard.
Oh, okay. The Wizard of Gods?
Yeah.
Okay. So the right-hand side, I mean, you can figure it out in your head. If you can, that's great. Because having good number sense, it goes a long way. But you do need to get to a point where you can get stuff right also. When you're evaluating a function, all you have to do is type it in exactly how you see it. So the right-hand side, I'm going to type it in exactly as I see it. All right. So I show the step where I'm plugging stuff in, and then I get the result. All right. That step on paper helps me kind of strategize how I'm going to put it in the calculator. But then after that, let the calculator do the work. All right, there are other ways for the calculator to do this work because, again, f of x is the same as saying y. So this is the same as saying y equals 4x cubed minus 17x plus 2. The connection being that if I'm looking for something like f of negative 2, I'm looking for the y value that goes along with the x value of negative 2 if I had a graph for this function. All right, so let's create a graph of the function. Get rid of all this other stuff. Something to look forward to in future years. So 4x cubed minus 17x plus 2. Ooh, plus 2. All right, at this point, you have possible avenues. One would be to go into your table. All right, second window. Take a look at the x value of negative 2, see what y value goes along with that. Coordinate negative 2, 4. All right, no computation required. All you did was type in the original function and then look for the x value of negative 2. All right, you don't like that? Another technique would be after you have your equation in there in y1. This is a very useful approach because if you have a decimal value that's being plugged in for x, it doesn't easily show up in the table. So what we would do, so the process in the calculator, I can't spell, which is weird because I was a 4th grade spelling bee champion of Dutchess County, so I probably should be able to handle stuff like this. Process, put function into y1. All right, so that's the y equals menu. So as if you're graphing it, because you notice we didn't even look at the graph. I got the answer, I didn't even have to look at the graph. All right. Then in your home screen, you're going to select alpha, then trace, and select y1. All right, so I put my function into y1. I typed it in the way they gave it to me, except I use y1 equals, they use f of x equals. It's not a big deal. In my home screen, so quit out of there. Now I'm hitting alpha, trace, selecting y1. All right, so that's referencing my function y1. I'm going to open a set of parentheses. I'm going to do y1 and then type in the -2. So open parentheses after that. Type in a -2. This is function notation for the calculator because I've told it that my f of x is in y1. And now I'm asking it to figure out y1 of -2. So I'm actually asking it to do what this is asking me to do. I'm asking the calculator to find f of -2. And it'll do it that way. The benefit of this approach is it doesn't matter what the x value is. If they wanted 2.5, if they wanted pi, all those calculations can be had without doing it by hand. All right. Benefit to having number sense, definitely. Being able to do some computations in your head, really useful. But I just think of it like technology. You know, there's some things that computers and apps can do that we could probably do manually. I mean, I'm pretty sure I don't need an app that tells somebody to go to the supermarket for me, buy all my groceries, and deliver it to my door, because I could just go to the grocery store, buy the groceries, and bring it home myself. But I prefer to have somebody else do it. It's a lot easier for me. Because you know what it involves? Me not having to go to the grocery store, buying all that stuff, and then bringing it home. All right, so for a few extra bucks, I can have somebody else do it. I like that, right? That's what this is. You don't have to do any of the work. The calculator's willing to do it for you, for free, no surcharge. All right, so in the second problem, y is now this, -9x squared plus 3x minus 5. Quit out of there because I have it stored in. I don't even, again, don't even have to look at the picture. I don't have to know what this graph looks like. Eventually we'll learn all about those types of graphs. For now, I don't even care. What I want is g of 1/3, alpha trace y1, type in 1/3, and you get your answer. All right. So g of, if you needed to show some work, this is what you'd show. The act of substituting. Replace the x with the 1/3. Write the answer. I mean, just thinking forward to the Regents exam. I don't know how much experience you have with Regents exams. But
Science.
what's that? Earth science? Okay, so then you know it's multiple choice and then a whole lot of stuff after that that's not multiple choice, right? So multiple choice, some free response. They break it up into 4 parts for some reason. Because they, you know, part 2 is like the short answer stuff that's not as hard as the part 3, which is not as hard as the part 4. But part 1 is all multiple choice. If you had a question that said g of 1/3, which of the following choices is equivalent to g of 1/3, you don't need to show even this step. You don't want to do that work. Just put it in your calculator, get the answer. You know the choice. That's the end of it. All right, so you got to buy into this stuff. I know we're resistant, and I know that some people, and this is not just limited to this class, this grade, this generation, or anything. People just don't always listen until they realize that the thing that's being spoken about is important, at which point they've missed all the instruction related to that thing that's important. It's like the big payoff at the end is like, oh, that actually seems like a really good approach. I should know how to do that. And then the absolute worst thing you could do is like, yeah, so can you like do all that again? Because then I know that you weren't listening the first time around. Because really, conceptually, there's nothing to get. There's not anything that you would not understand if you follow along. Put the function in y1. Go into your home screen, hit alpha trace y1, and then type in your expression, whatever it is you're evaluating in terms of, in this case, -2, in that case, 1/3. All right? Now, it changes if you're evaluating in terms of another variable. If I'm plugging in like an a plus 2 instead of a 1/3, calculator's not going to help for that. But for the numerical cases, absolutely. And you could even think about cases where, you know, just going back to the last unit where it would say something like f of 2 minus g of -1. All in one shot. You can get it done. All right, so definitely worth looking into. All right. So we're going to learn about the structure of a polynomial. And there's a few important components. The vocabulary helps us to kind of understand these things. This is the language that we speak in terms of when dealing with polynomials. So the sooner you get up to speed on this, the better off you'll be. So a term is a single expression that does not involve addition or subtraction. All right. So, example. -2x to the 4th power. I'm not adding it to anything. I'm not subtracting it from anything. Don't get a negative sign confused with subtraction. All right? A signed number is the quality of that number. This is a -2. I'm not subtracting it from anything. If it were 1 minus 2 to the 2x to the 4th, then it would not be a single term. You'd have more than one term. All right, so if I had something like, let me do that in red actually. 1 minus 2x to the 4th. This is not a term, it's two separate terms. I have a term here and a term here. So this is two terms. All right. Very rarely does anybody ask you to actually count up the number of terms that are in an expression. It's kind of a filler type question, but I mean, I suppose it could come up. If that's the case, really what you're doing is just taking the number of plus or minus signs and adding 1 to it. So if I have 1 plus or minus sign, then I'll have 2 terms. If I had 10 plus signs, for example, I'd have 11 terms. So it's always one more. Right, but that's not something, I don't think you need to memorize a rule for that. You just look at it. All right, coefficient. Numerical multiplier of a single termed expression. All right, so if I'm just focusing on a single coefficient, I'm only working on a single term. All right, so if I had something like, I mean, I just take the same example. -2x to the 4th. That constant multiplier, that numerical multiplier, would be the coefficient. All right. So you have a variable part, and then you have the number that's being multiplied by the variable. We call that a coefficient. All right, constant. A constant is a standalone numerical value. All right, also known as a fixed value. So if you see in a word problem, constant or fixed, it means the same thing. All right, so if you had something like, I'll go back to the other example that I had, 1 minus, I hate when that happens, 1 minus 2x to the fourth. This would be a constant. All right, doesn't have a variable attached to it. Attached would be through multiplication. All right, so if it's a lone numerical value, a term that only contains a number, no variable, then you're looking at a constant. All right, a monomial, algebraic expression thus containing only one term. All right, so an algebraic expression containing only one term. So the example that I used for constant, that would not be a monomial because there's two terms. All right, the constant represents one term, and the 2x to the negative 2x to the fourth would represent a second term. All right, so a monomial, negative 2x to the fourth, not 1 minus 2x to the fourth. All right, the number of terms is defined by the number of addition or subtractions. If there is no addition or subtraction, then it's only a single termed expression. A monomial could be as simple as just a plain number. All right, so the number 2 is a monomial. But it could also be something more complicated, like 2x to the 15th power times y to the third power. All right, does not contain addition or subtraction. That's the only condition.
Can the monomial also be a term?
Yes, a single term is also a monomial. If you have more than one term grouped together, then it becomes what we call a polynomial. Mono, poly.
So how would you know the difference between if there's more than one?
If there's more than one term, then it's not a monomial. All right, so the polynomial, algebraic expression containing more than one term. So, in this case, 1 minus 2x to the fourth would be a polynomial, but not just the negative 2x to the fourth. I mean, there's many, many examples of monomials and polynomials. I'm just kind of bouncing back and forth between these two. But this has more than one term. This has only one term. So this is a polynomial, that one is not. This one only has one term, so monomial, that one has more than one term, so that can't be a monomial. All right. Degree It's one of those words that I kind of wish they had a different one that was commonly used, because it could mean so many different things. Degree could be a measure of temperature, could be a measure of an angle, and in this context, it's neither of those. It's the highest power in any polynomial. All right, highest power in any polynomial. So what we would be doing is we would be looking at all the terms of whatever the polynomial is and identifying whatever the highest power is that's contained within it. All right, so you could have more than one or two powers. You know, you could have like 10 different powers. So let's say you had something like, I'll expand upon my previous example, 1 minus x plus x squared minus 2x to the fourth.
What if we added 2 to the 7 in the example that you did?
If you added a 2 to the what?
To the power of 7.
2 to the power of 7, like as
Yeah.
an extension,
Plus.
then that would change the answer. So at this point, we would have the highest power being a 4, so our degree would be 4. But if you added 2 to the power of 7, now it's a degree 7. So whatever the highest power in your new polynomial would be, that is going to be the degree of that polynomial. Right? So if I had, and it doesn't matter what the order is. So I could have something like x to the 8th minus x plus x to the 9th minus 2. What would be the degree of that one? 9. We're just picking out whatever the highest power is. Right. The leading coefficient, this is kind of a sort of a misnomer, because the leading coefficient is the coefficient associated with the term with the highest power. And this is the source of pretty much any trick question in this unit. Right? Because the example, or an example, would be something like, we have 1 minus 2x to the 4th plus x to the 3rd. So what would my leading coefficient be there?
X.
Well, that's the thing. A coefficient, by definition, is a numerical multiplier of a single-termed expression. So it's a number, not a variable. So it's the number that comes in front of a variable.
2.
Negative 2. Okay, so you're looking for the term with the highest power. In this case, the negative 2x to the 4th. So that's this one right there. The coefficient of that term. It's misleading because it has the term leading in it, which makes you think that it would be the first one. So if you look at this and you said 1, That's because that was the first coefficient that you saw, and you thought leading coefficient meant the first coefficient. So you need to kind of adjust your mindset here. It's not the first coefficient you see. It's the first coefficient you would see if your polynomial were in the proper order. The proper order would be the term with the highest power first, then the next highest power, then the next highest power, and so on. This is out of order. If you were to put it in order, your leading term would be negative 2x to the fourth with a coefficient of negative 2. But instead of rearranging it, all we have to do is look for the highest power, then within that expression, that monomial, identify the coefficient. All right. Now, the standard form of a polynomial, that's just, it's an FYI for now. It's f of x equals a times x minus h to the nth plus k, where your leading coefficient is a and your degree is n. This one, it's a fact for now and not meant to be understood, but because we're compiling all of our terminology into one area, even though we're not anywhere near where we would have to be in order to understand this, we still just write it down here just so we have it. All right. Monomials that have the same variable factors are called like terms. So basically, if they're made up of the same variable stuff, then they're like terms, and then you can combine them. So you see each one of these has an x, y. Forget about the coefficients, not important when it comes to like terms, just the variables. Do the variables have the same structure? And so basically, is your monomial or all of your monomials made up of the same variables with the same powers? Here, x, y, x, y, x, y. Here, a squared, b cubed. Same deal here. But here, they're not like terms because even though I have x's, they're all raised to different powers. All right, so definitely not like terms.
But negatives are still like terms.
Mm-hmm. Exactly. So if you're adding polynomials, it's really just a matter of adding the like terms. So all that vocabulary aside, it's pretty simple when you think about it, because all you're being asked to do is identify the like terms, and combine them. All right? So only the x squareds can be combined with one another. So these two can get combined, these two can get combined, and these two can get combined. So if I add 4x squared and 2x squared, what do I get? 6x squared. All right, we're only adding the coefficients. If I add, this is an assumed 1x, understood coefficient, number in front of the x, even though it's not written there, it's assumed to be a 1. 1x plus 3x, 4x. And then the last part is simple because that's just, there's no variable there. 7 plus 1 is 8. All right, sometimes our coefficients, our terms don't match up from parts of a sum. So here I have an m squared, but no other m squared to combine it with. So I'm not going to worry about that. But I do have some other like terms. So nothing to combine with the m squared, so that'll be part of my answer. Negative 10m plus 8m would give me what? Negative 2m. And 5 plus 2 is 7. All right, sometimes the powers get a little crazy. crazier, but that doesn't mean the problem gets any more challenging. Identify your like terms. 2y to the fifth and y to the fifth. Give me what? What's 2y to the fifth plus y to the fifth? 3y to the fifth. All right. I look for something to combine with the negative 6y to the third. I have something to combine with that. But before I really address that, I may want to account for the fact that I have a lone 8y to the third here with nothing to combine it with. I'm sorry, 8y to the fourth. So plus 8y to the fourth. Then I'll combine my y to the thirds. So negative 6y to the third minus 2y to the third. Negative 8y to the third. And then positive 1 and negative 1 will add to give me a 0, so that's going to cancel out. All right. Nothing to combine with the 5. I can combine a negative t with a 9t to give me what? 8t. And what happens when I take negative t squared and add to it a t squared? Nothing. You get a 0. All right. We're looking carefully at each expression and identifying the term with the highest power, because we want our answer to be in what we call descending order. Highest power comes first, then the next highest power, then the power after that. So just take a quick scan and take a look and see what the highest power is here. In this case, negative 7k to the fifth. Is there a counterpart to that? Yes, there is. But if I add those two, what's going to happen? They cancel, so get rid of them. You can cross them out or just ignore them. The next highest power involves a power of 3. If I add the corresponding terms with power of 3, what do I get? A cancellation. All right. So the only thing that's left is a negative 3 and a positive 5k squared. All right. They can't be combined because they're not like terms. But also, again, I want to have it in descending order, meaning I want the term with the highest power to come first. So this would be 5k squared minus 3. All right. Some questions don't care about the order of your final answer, but some of them do, just thinking in terms of a multiple choice question. You come up with that, but that's a choice. You got to know that they're equivalent. All right. Number 6 adds a little twist to it. We have the 3p plus 1, that's fine, but then here I have a 6 times p minus 8. What do you think I ought to do there? Distribute. So I'm looking at 3p plus 1 plus 6p minus 48 plus p plus 2. So I'm dropping all the parentheses because, as it turned out, they didn't really make a difference. Right? They didn't serve any purpose aside from showing me that I had to distribute here. Once I've done that, I'm good. So then I'm going to combine my like terms. What do I get when I add those together?
9p.
10p. And then 1 minus 48 plus 2? Negative 45. All right, subtraction of polynomials. All right, so we have opposites. I'll just do a couple examples here because time-wise that's all we need. And also that'll set you up for the homework. If I'm looking for the opposite, all I'm going to do is negate each part. Yeah. So all your positives become negatives. Any negatives become positives. So the first one was a positive x squared, so it becomes a negative x squared. The second one was a positive 7x, so it becomes a negative 7x. All right. If they were negative, I'd make them positive. So that part's easy enough. when you're subtracting polynomials, you're involving opposites. But more importantly, if you just remember to distribute the sign, everything tends to work out. All right, so negative 4x cubed, and then negative negative becomes positive. So then we just combine our like terms. It turns out we don't have much to combine here. 2x cubed minus 4x cubed is what? Negative 2x cubed. I don't have anything to pair with the 4x. I'm going to like terms with the negative 2 and the 6. That's going to give me a 4. So 3x cubed.
And I have trigger. Yeah, I also have trigger. You're not in my trigger. Yeah, but I have trigger.
So 6.
Please go to the bathroom.
Can I go to my teacher for something? I'll be back in a minute.
Squared plus 20.
So bad. She's cooking